Thank you very much, Peter. Can you hear me? So this is working. Okay, perfect. So I just realized when I saw myself on the screen there that I cannot move here because then I will not be on the video. But you're managing it. That's even better. Okay, so nobody needs to warn me. Okay, so yeah, thank you very much. Today I will talk about what I call here intelligent decision-making under uncertainty. And I realized when I was preparing these slides that I don't really want to talk about this picture now, so I chose another one. So with this, I want to thank the organizers to invite me to this, give this keynote here. I'm very honored and very happy to do this. And this advertisement for the best, what Germans call Fischbrötchen in the world, which I had here at a certain restaurant. I don't know if I should do advertisement here. I can do this later here in Lübeck. Okay, let us see what I want to talk about. So I usually start with the motivation why AI systems are extremely important in our life, but somehow I fear that everybody would agree on that. So again, I chose another slide for this part, which is what many people are interested in nowadays, and I think there was a special theme in this conference too, to kind of talk about the marriage between formal methods, in my case, mostly verification, and artificial intelligence. And in this marriage, many people usually talk about aspects like formal guarantees, structured semantics, well-defined models, specifications, scalability of approaches, and safety. And this is by accident diamond-shaped, and then I put a diamond over it. So this, I may have worked on these slides last night. Okay, so let us move on. So in the past, I attended and organized quite a number of events that wanted to bring together people from formal methods and AI to have a more focused discussion on what is really important, what can you really do. So there was a Dagstuhl workshop, there were several workshops at conference, a Lawrence Center seminar, and there are 2 Dagstuhl seminars upcoming that I'm organizing also. I'm not listing events that I attended that others organized. The problem was a bit that in these discussions, when it was not only formal methods people with a certain background who basically want to do some AI, it became apparent that not everything is really clear, not everything is really well defined on what we actually can do, what we can do with formal methods. So at some point, I kind of got the feeling that it's not really a marriage, but is this visible? Barely, right? I cannot do something about this. So it sounds a bit more that the formal methods area is sometimes kind of proposing to the AI area, and AI can be machine learning and other more traditional approaches. Because questions that we usually get when we tell them, hey, we are formal methods, we give you all the guarantees that you need, then what happens that they ask, what are guarantees? What is this specifically? How do you even get your models with which you work? What are meaningful specifications? How can they actually help us? How scalable are your methods? And what I get quite a bit, what actually is safety? Because I mean, many of you have seen approaches, safe AI, safe learning, safe, everything is safe. And we will talk about this more. Okay. To make this a bit more specific, I learned recently that I'm actually not working only on the area of bringing together learning and let's say formal verification in this case, but that I'm also working on a more broader and a bit more fancy sounding theme, which is called Neurosymbolic AI, which integrates neural and symbolic AI architectures. And in some sense, the symbolic AI architecture that we see here is to use a structured model of a system and perhaps give some structure and some guarantees using verification / formal methods. And we will talk more about this. What I also learned very recently is that I'm actually working on digital twins. I didn't know this, so I can add another buzzword to what we're doing. Because the digital twin, if you consider the system from which we are learning here, could be some form of a cyber-physical system. We learn something, we may then obtain or have built or have kind of gotten in the beginning a model, for which again we can do some verification. So we have some confidence that this model actually is in some form a digital twin of the original, let's say, cyber-physical scenario. So I have 2 new buzzwords that I can add to my research here now. Okay, let us now talk a bit more in detail. I was talking about safety and what safety could mean and what it should not mean. So in the very traditional sense, safety for me means that nothing very bad happens. So in these applications, we see the delivery drone from Amazon. It should not crash into a building, right? This is obvious. This would be unsafe. Also, if we have the, what I always say, unavoidable autonomous car, it should not crash into a pedestrian or a cyclist here, right? And then not doing this also depends on a proper sensor reading of obtaining the position of these let's say, participants in traffic. And one of my favorite examples is about spacecraft, where we say, hey, there's a satellite, it should not crash into other objects in space, and believe me, there are many. And I mean, this aspect of safety in artificial intelligence has been recognized all over the world. Many agencies, a lot of, let's say, position papers have stated this fact, which basically say your method needs to be safe, right? Now, I kind of always have a problem with the terminology here, and I'm listing a few examples here, because safety is totally overused, because it could also mean that your AI method should be robust. It should work in a dependable manner. It should be certifiable. It should be correct, reliable. So I always struggle with finding the right words, so I'm just using all of them sometimes. What we basically, I think, want to do usually is to say that our AI method or AI system works or behaves as we intended to, right? And then, of course, we need to think, how can we actually formulate the intent that we have for this system? Yeah. So this is kind of a mentioning that I might use different words for the same thing throughout this talk. Okay, let us move on. The outline is that I will first give a bit of the general picture, the vision, what we do in decision-making under uncertainty. When I did this and I kind of have established what we want to do, I will talk about a few challenges that I see and also about some research highlights, what we did in the last years. I will lose a few words about teaching, and finally I will try to wrap everything up. So let us see. Neurosymbolic AI. As we said before, neurosymbolic AI tries to integrate neural and symbolic AI architectures, and what is important to me here is that we want to address complementary strengths and weaknesses, right? So we kind of need to identify, if we want to, coming back to former methods and AI, want to see, okay, what are the strengths of former methods, what are the strengths of AI, and what are the weaknesses, and can we somehow bring those together? And this is something that we are really trying to do. So in this setting, again, we have some form of a model. We can perhaps verify it. Then we might want to give some input from this to learning, and then we might perhaps want to update the model. This I'm going to specify now. So to work on this in a structured way, we actually tap into several research areas because there are certain, again, strengths and weaknesses in all these areas. So we look into formal methods, and in my case in particular, rigorous model-based verification. In some sense, it's mostly model checking, but there are also some other areas. In AI, we look into the broader area of decision-making under uncertainty. From the control theory area, we look into particular control for continuous spaces. And from robotics, we try to get a bit inspired, get some case studies, and also learn about what are meaningful problems that we want to work on. So then I somehow need to connect these areas because this seems a bit all over the place. What does connect them very often is that we need to reason about the uncertainty that occurs in the real world. Yeah? So in some sense, our methods aim to and want to reduce the uncertainty or be robust against uncertainty that occurs when we work with real-world scenarios. So a bit more in particular, coming back to this loop about a model learning and verification, what you see now is a slight addition that we might have a partial model, right? So it's often deemed unrealistic that we have a fully specified correct model of the real world scenario that we have. So let's say we have some partial information that we can formally capture in a model. We may have obtained this using learning, and then we can verify something, but then we want to loop back and say, okay, we can use our structured information now to update the learning and then perhaps update our partial model, right? So one specific example can be that we have, say, a model, we have a certain, let's say, probability to go to some safe space, and we don't have a perfect model, so we cannot exactly compute this probability, so it makes a lot of sense to say, hey, we cannot give you an exact result, but what we can give you is perhaps an upper and lower bound on certain failure probabilities, for instance, and with these we can work very well. And to come back to the control theory aspect here, many of the verification methods that we use actually are built upon control-based abstractions and robust optimization techniques. So what we really want to do is we want to integrate these methods, verification and learning, to make them robust against uncertainty under real-world conditions. So this is our very general scheme. Excuse me. Okay. Moving on, this is a kind of toyish example which makes it a bit more concrete what problems we're dealing with. So what you see here is Amazon's delivery drone, and it wants to deliver a package to one of the buildings that you see here. While it's doing this, it encounters a lot of uncertainty. Like it's very natural. We make this rather specific here by saying uncertainty can be caused by sense or imprecision, right? So we may not be able to exactly detect the position of an obstacle, a moving or non-moving obstacle. Then there might be uncertainty about some wind that can impede the path of the delivery drone. And of course, there's a limited view because we operate in crowded environments, also called contested environments within this urban area. And we have a, for AI standards, rather complex task specification, which is in words, almost surely always return to the halting pad. So this is the yellow thing over here. After a delivery, and a crash is only allowed to occur with a probability of 0.001%. And we can put any number here. It doesn't have any meaning. This is just for us. Let's say this would mean safe for us. Yeah? And below you see this specification, how we can call it here, task specification in temporal logic. So the question is then, what are the challenges if we want to provide guarantees on the behavior of the agent? And the agent is actually the delivery drone in this case. Yeah? So how can we actually ensure that if this drone operates in the real world with knowledge that we have, will operate while satisfying this specification here? So this is one of the, I'd say, major problems that we deal with. So yeah, so the question would then be, if we specify this a bit, what are the real challenges that we have? And many of them remain and are not solved. People work on those, but it's not that there's like the kind of the accepted solution to such problems. The one thing is, and we all know this, that there is a scalability issue. So if we kind of increase the number of features that go into our problem, let's say the altitude, the temperature, let's say 100 other moving objects that fly around there, humans, everything, then this becomes extremely high dimensional and not scalable anymore if we want to like capture the full scenario. Another challenge is that we are not actually dealing with the usual, what people use, kind of toyish grid world examples, but we move in a continuous space where we actually, okay, we're not hopping from grid to grid, but we're actually moving continuously, right? So this makes the problem harder both in theory and in practice. As we discussed, we are dealing with uncertainty and in particular often partial information about the scenario, and we don't have perfect information at some point, but there's new data incoming. So we need to deal with data-driven problems, right? So we need to give guarantees in a data-driven way. So these are the challenges, how I identify them. You might disagree, you might add others, but this is a specific view that we want to take here. Okay, so how to solve these problems? There's a major machine learning technique called, or say area reinforcement learning. I think most of you have likely heard about reinforcement learning. Formal methods, people often love it because it somehow comes close to what we understand. This is what I think. So what does reinforcement learning do? An agent explores its environment by taking actions and observing certain feedback signals. This can, for instance, be, I go here, and then my feedback is I'm a bit nearer to you, and I get some reward for this because now I can see somebody better, right? So this is the information that I would get. And what is kind of a drawback of reinforcement learning that for me, took some time to really grasp this. It's not that you're just collecting data and finding the best decisions, but you do this in a way that you have some form of a halting criterion. So at some point, you will stop and start again. You will stop and start again. Stop can be if you reach your goal, if you crash. This can be a lot of things. But what it means also, that is very tricky in a real-world scenario because you don't want your robot to move up there and once it crashed here, move up again. Crash, move again, right? So you cannot restart all the time, right? This is nothing you would want to do. And what it also means is that it will in the beginning, in what people call the exploration phase, try out everything that you could do, right? And this exploration is extremely safety critical because if you don't have any information, no structured information about your environment, there's no means to know what happens upon doing a certain action. So exploration is very safety critical, and here really I mean safety. Reinforcement learning is also, despite all its success stories with, for instance, AlphaGo, extremely data hungry, right? Not everybody has a Google DeepMind kind of computing power at its disposal. And so there might be just the problem that it would never converge to something, never meaning in a reasonable amount of time to something that you wanted to do. And in the standard reinforcement learning setting, you just have rewards, which mean you observe the reward of a certain action, and these can at least basically not cover more sophisticated specifications like the ones we saw in the beginning. In particular, what is very hard to encode is some repeated tasks, right? So do this again and again and again until you do something like this. Yeah? Okay, so this is reinforcement learning, extremely famous, extremely successful, but there are a lot of major drawbacks that, by the way, not only formal methods people acknowledge. There are a lot of standard position papers that you can find, especially from the robotics area, which state exactly those problems for RL. So what we deal with is formal verification, particular model checking. Let's say we have a very nice model of our environment, and then we can use methods to prove the correctness of the model regarding a specification that we have. And in the type of models that I use, which we call often uncertainty models, we have a lot of rigorous numerical techniques to prove this correctness. And the models are called, for instance, Markov decision processes. We deal with extensions that capture richer types of uncertainty, partial observability, or adversaries, where we move to a game-based setting then. The limitations of model checking are mostly well known. So one of them is that the underlying problems are often very hard, often even undecidable. So there's a problem with scaling model checking to real-world scenarios. For me, a very serious limitation is actually the question, how do we even get our models, right? So how do we get a model that we can trust to capture the real-world scenario that we are dealing with? And again, how can we integrate this kind of this theme that we have a perfectly well-defined model, right, in a data-driven setting with incoming data, right? So this makes it very tricky to do these model checking techniques, yeah? So we've established reinforcement learning, model checking as kind of complementary techniques, and these we, in some sense, want to bring together. So what is our very concrete research objective here? We want to, I say, elevate the state of the art in safe and correct decision-making for AI systems. And at some point, I started to adding the and correct here because safe was just being too overused. And I can talk about this later if you want, about the misuse of the word safety. A bit more particular, so what we want to develop are verification techniques that are scalable and data-driven. We want to integrate them tightly with reinforcement learning, and there are a lot of challenges under real-world conditions that we actually aim to address. This is our more general vision that we are working on. Good. The outline. I want to talk about some a bit more concrete challenges and want, of course, also to show some research highlight that we have been working on. So let us start. We made some progress over the last years, and perhaps also coming back to this problem of formal methods proposing to artificial intelligence. But this is my personal opinion. I think what makes a lot of sense is not only to tell people, hey, we have all these beautiful methods, use them. They do what you need, but rather to try to really work on problems, to integrate with problems, and this is a very particular challenge, to also publish in their conferences. And I can tell from experience that this can be rather painful because in the beginning, it was like 4 or 5 years ago, we had a lot of rejections, basically because we didn't know the terminology or how to write a paper. So, I mean, you all know a typical formal methods paper, definition, 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 then 10 pages later, as stated in definition 3, and so on, and they hate this. But because I think we've been, what were the comments? This paper largely consists of fake math. What was the other comment? This paper nearly reads like code. So I mean, there were more of these comments, and this was a bit frustrating, but at some point, I think you can find out also how to go into these areas. And what is, for instance, very promising that the largest general AI conference, AAAI, last year had a track, perhaps many of you know, which was called something like Robust Artificial Intelligence or Robustness in Artificial Intelligence. They had a huge number of submissions, many of them from people with a formal methods background, and also many people with an FM background were reviewing there. I'm pretty sure that some of you have been reviewing in this track last year. And many got accepted, so this is nice. So there is some recognition about the things that we can do, and I think it's also very nice that this is happening nowadays. Okay, let us first talk about one of the major challenges that I've been talking about, which is uncertainty and partial information, and what we want to and have done there in the last years. So a big challenge, as I mentioned, was to get any models. And in this case here, want to obtain models that deal with uncertainty. So the very general problem is we want to learn a model and then we want to analyze it. yeah, in a rigorous manner. So we learn this from data or some samples, for instance, obtaining by actively probing some system. We want to robustly capture uncertainty and probabilities, and I will talk a bit more about the difference between just probabilities and uncertainty. We want to account, and this is kind of what people sometimes call a holy grail problem in AI, to account for changes in an environment, right? So we learn from some environment, which could be a simulator. So what happens if the underlying model that the true model that we learn from just changes for some reason, right? So this is a very tricky problem because then what we learned so far might be meaningless or not really valid anymore. And we want the model to be amenable to efficient model-based analysis, which also means that we need to think a bit about scalability and how the model is defined. Yeah? And I've tried to draw this here. So we have a model and we have a system. The system, let's now assume it's larger than the model, and the model is really inside the system. So we draw data from the system and use this data to refine our model. And with this one, we can analyze or verify, as we can also call it. So what, more specifically, what we tried to do was, there's a larger effort to learn these models that are called Markov decision processes, right? So I hope most of you know what an MDP is. It's basically a model which captures taken action, and then there's a stochastic outcome of taking certain actions, yeah? These models have been used for many, many years. There's not a lot of, but several very well-known tools that deal with these models. There's, for instance, the Storm model checker. And Peter is sitting in front here. I don't have a picture of Storm yet, but I will, no worries. And there's also the Prism model checker, which is being developed nowadays in Oxford by Dave Parker. And these MDPs, they have a problem. There were a lot of benchmarks, big benchmark suite, but somehow, when I was a starting PhD student, I sometimes got the question, I remember this, my second ever conference talk at ADVA 2011, perhaps in India. So I said, where do you get the probabilities? And I didn't have any answer. I just said they are in the benchmarks, so they must be good, right? And perhaps some of you have asked yourself this question, so how realistic are these benchmarks? So let's now assume that these probabilities are realistic. Then they're still somehow either designed or derived from data. And what this means, if we just kind of have one probability that captures a setting that comes from a lot of data, then we will get statistical errors. And it's been shown, and it's also very obvious, that this is a problem because it can lead to very unsafe decisions if we just base our decisions on this one probability. And also, again, what happens if our environment changes? Then how can these point probabilities capture what we actually want to do? Yeah? So what we try to do is we want to learn models with richer uncertainty. And the very simple version of this is don't have a point of probabilities, but have an interval of probabilities that more robustly capture the statistical error that our derivation can have. We want our learning scheme to be adaptable, right? So if new data comes in that doesn't fit with our current estimate of this interval, then we want it to be adaptive. And what is important for me is, and this was actually a hard time to explain also to people from AI, was that we at any time, if we have this model, can compute a policy, which is kind of a decision-making theme that is robust against this uncertainty. So a bit more specific what this means. We have this model with all these ranges of probabilities here. So what we can do now, we can give you the best policy decision-making scheme that is the best no matter what happens within these intervals, right? So no matter what the actual probability of our system is, we are robust against that. And this is very easy. This is done by a robust form of value iteration, very efficient. So this is something that we can very easily do. So a bit more specific, what we do is we use a reinforcement learning scheme called robust RL optimism in the face of uncertainty, which is a bit bad because what this reinforcement learning method does, it always assumes within these ranges of the uncertainty, we assume that that is the best for us will happen. So this is not robust, it's really optimistic. Yeah, and then we use this to collect data. We use the data to update our model, and then we can at any time, so there's an anytime algorithm, compute our policy. Then based on this information, we can then update our model. Yeah, so this is kind of neurosymbolic it is neurosymbolic because we have our AI method, we have our symbolic method, which is based on this model, and we exploit it to update the learning process. A bit more specific. So perhaps you have heard about PAC learning, probably approximately correct learning. And what it does, it estimates in probability, yeah, and then it puts a margin around it. Yeah, so this is a confidence interval. And with this scheme, you can give guarantees on how faithful the model is to the actual environment. The problem with pack learning is it's very conservative, right? So we might get very large intervals, and also it's extremely data hungry if you are aiming for any statistical guarantee on how that your model is faithful in the end. And for me, at least, more serious, that it's not adaptive, right? So it cannot recover if the environment changes. So we proposed it what we call linearly updating of intervals, and the very simple idea here is that we don't see intervals as a point with a margin around it, but we see the interval as two separate points that form an upper and lower bound, which we update individually, right? So we parameterize our method by the interval bounds, yeah? And we update them individually, and this can easily, I'm not putting the details here, but this can easily update and also recover from changes in data, right? So very simply in a sense, so let's say we converge to a small interval, and then something happens that doesn't really fit with what we have been doing so far, so our scheme automatically enlarges the intervals again. Then there are a lot of hyperparameters that we're using, which is, for instance, what prior do we use, what is the strength of the prior, how much in the path do we look, how much do we value the path. These are technical details, which are, of course, very important for the performance, but I'm not talking about this right now. So some results. So the first one is, let us say we have our true model that we are learning from, and we estimate this model via these intervals, right? So a very obvious benchmark is to find the policy that is, despite not having these precise probabilities yet, we can find the optimal solution based on the intervals. What this means in some sense, that our decision making does not depend on precise probabilities, but on basically on this is enough, we've learned enough, right? So this is very efficient in the end as opposed to point-based learning. So what we just see is that it's competitive against other approaches, which are point estimation, robust reinforcement learning, and pack learning, right? So it can usually find the optimal solution a bit faster than the other methods, as we see, for instance, here. This is the blue line. This is our method. So it starts with a very small value, and then it increases to the optimal solution about here, right? So this was nice. This showed us, okay, our method is effective, and it doesn't always matter to have these precise estimates, but this was, for me, not the most important feature. For me, the most important feature is really the robustness against changing environments. So what happens here? By the way, now we're minimizing, right? So less is better. So what our method does, the blue one, right? So let's say at this point where you see the arrow, the environment changes, the underlying model changes. It's a new one. We chose this arbitrarily. It can be a huge change. It can be a small change. This doesn't really matter. So what happens? Then the performance of our method really drops. And it's very obvious why this happens, because we just enlarge our intervals, right? So we have very conservative estimate. But then, by collecting more data, we tighten them rather quickly and then recover from this change and go towards the optimum. All the other methods, and this is also clear because of how they're working, will not recover from this. So you see, for instance, that the point estimation will just drop a bit and then stay at this performance. Robust reinforcement learning will just kind of always stay the same and sometimes fluctuate a bit. But in the end, excuse me, what we see is this method is adaptable to changes in the environment, and I find this very important in the setting. Okay, so if you're interested, you can read about this in our newspaper from last year. I think it's not published yet, but there's an archive version online, and of course I'm happy to share and discuss about it later if you are interested. Good, let us move on. Another thing that we were interested in some sense, was to make neural networks robust against many environments, many changes in the environment. And my problem was that I never really understood neural networks, and I think I still don't. So we need to find an approach that helps us train the neural network based on our structured model-based information, which can, for instance, be that we deal with a family of these uncertainty models. We select some of them and use them to train a neural network. Yeah, and then we can analyze it. And then we can perhaps use some what we can call diagnostic data, counterexamples, some adversarial parameters to retrain our network to make it more robust against a whole lot of environments that could actually be the real environments, right? So this was something that I've always found a very interesting problem, and I will tell you about our approach. So I've said before that neural network robustness for me is very important, but it's also a very hard problem. So does anybody here work on neural network verification? You do. Very nice. You. Okay. More. Okay. So what I gathered, it's for me I've tried to work a bit on it. I found it a very hard problem because at least the methods that I've seen at this very limited view, for instance, based on SMT solving, are a bit limited in scalability. Because it ultimately, if you have a huge neural network with a lot of layers, there will be a scalability issue, right? And of course, I'm pretty sure there has been progress in the last years that I'm not really aware of. But let's just say it's personal. For me, it was a too hard problem. Then I was working on marker precision processes, in particular partially observable marker precision processes, where everybody told me 5 years ago, stay away, everything is undecidable, right? So very bad for methods people, it's undecidable. While robotics and AI people have been using them for years and kind of just using some learning method or restricting everything to what we call finite horizons to make things decidable again, right? So they have been used a lot. So, but we still, everybody acknowledged it is a hard problem. So what I observed then at some point is that actually in reinforcement learning, neural networks are used to represent policies for these POM-DPs in a very efficient way and also in a data-driven way. So there must be something how we can put this together. So what our idea was is kind of assess the robustness of the neural network in a fixed environment that is modeled by a partially observable MDP. Right? So from this we started and we thought, okay, this could be very simple. We just have some model, we can do some verification. It turned out later that there was a much more intricacies to this, but I will try to talk about a few of those here. So this is our general setting. We have some POM-DP model. We have some, if you want, very complicated task specification. You have your neural network policy, that is a policy for this POM-DP. This one you want to verify. Does it satisfy the spec or not? Questions are, what is the suitable neural network architecture that we can use? Can we somehow not only assess its quality, but can we perhaps also use our result to improve the training of the neural network, right, to make it perform better? And then, and at this point, if I have this slide, I always say, I'm very reluctant to say we want understandability, explainability, and so on, because I find this a hard to grasp problem. But in some sense, we want something that we can better assess than a neural network, which I really don't understand. And perhaps algorithmically important, the policy that we kind of get should not directly be the neural network, but it should be easy to verify. Good. About this, so what we use is actually as policy representations are so-called finite state-controllers. They are, in a sense, randomized Moore machines. So we have an input, we have an output. And what happens here is that what the state machine does, it gets an observation from our POM-DP model and then says, okay, choose this action, perhaps with a certain probability. This is a finite state controller. What is nice about it, that this is a well-defined policy representation that we can use to combine the two entities, the model and the policy, in a product, which of course grows exponentially, and then we can easily verify this. So what you see here is not a complicated POM-DP model anymore, but this is a Markov chain which we can very efficiently analyze. So how do we use these? We have our POM-DP, we have our spec, and we have our neural network. So how do we train the neural network? We use some policy to generate some data on the POM-DP, and this can be done using reinforcement learning, of course. So we train this using some learning method. What we do next is we extract this finite state controller, yeah? And something to mention here is that what we do using this extraction, we give a bound on the number of memory states that this memory structure, this finite state controller can have. So let's say it's 10, yeah? And of course there's imprecision involved. And we can increase the number of memory nodes, no problem. But we start with something that is reasonable for the analysis. Well, when we have this, we compute this product, we get a fully probabilistic model, and this one we can very easily verify, for instance, using Storm or Prism, yeah? Or even in small examples, your own coded method to solve a linear equation system. So now, this was not satisfiable, so the question for us was, if it's not satisfied, what do? We don't want to stop there. So what we do is we use the information we get from this verification to select some, what AI people would call adversarial parameters, what we would call a counterexample on the actual reason for that this spec is not satisfied. Yeah? So we use this information to generate some new data, yeah, and then we iterate again, right? So we could now iterate until hopefully we get to this point. The problem is actually in the precision of the finite state controller here, because if we always extract a finite state controller with 10 states, it might never improve, because the problem was not actually in generating new data, but in the imprecision of the policy extraction here. So our heuristic here was that we say, well, we have this model and we have these distributions of choices that we made. So we have some very structured information. So can we use this to assess the level of training of the neural network? And our perhaps very, let's say, naive assumption here was if the entropy of these decision-making at certain critical states is very low, right? So in a sense, if it's low, I always confuse these, but if it's low, it means that we have probably a uniform distribution over actions. Then this means, well, the training might be very nice, so there are some decisions being, no, it's the other way around. Low entropy is basically a Dirac distribution. Thank you. So I usually have a cheat sheet here to remember what that is. So now if we have kind of a Dirac distribution, that means, okay, the neural network makes very informed decisions, but now the problem might be the precision of the extraction. So then we increase this. What we can handle using analysis, of course. If it's high, then it seems like it's making arbitrary decisions. Then we want to increase the level of training. So this was our heuristic. It worked quite fine, sometimes not, as it goes with heuristics usually. So you can see this here in this ideal picture, and I was at some point only showing this one, then we used more case studies. What we see here is, this is the probability of satisfying our spec. This is the number of critical states in our model that we extract. So what this means is the probability of satisfying goes up, the number of critical states goes down. Perfect. Our heuristic works perfectly. Other cases it doesn't really, which is natural. Also, this is a very hard benchmark for this method. But still, it always converges to a nice solution in the end. Disclaimer, this is of course not a complete method. It's a sound method because we can verify the policy that we extract, but we have to be realistic. This might not converge to something optimal. Okay, let us move on. Does it scale is the obvious question. Very quick answer. Often yes. So you see here a benchmark with 4 million states, and this is way beyond what at this time any POM-DP solver could on its own handle, right? So this really helped. Disclaimer again, this might not be the optimal solution, but it is a good one because we satisfy our specification that we have. Okay. There's some literature, the kind of most recent one in the Journal of AI Research from last year. Yeah, it's actually 2 years, no, I think it's last year. Sometimes this is a bit unclear with the publication date. If you're interested, have a look or talk to me. Okay, let us move on. I want to talk a bit about continuous spaces. So, and this is something we only started 2 years ago. Many people of you might have worked on hybrid systems, for instance. I have not, so, but we always kind of acknowledge that this is an important problem to go a bit away from the toyish examples, this discretized world that we have been living in. So what is our challenge? We want to use some data-driven verification and abstraction method that can somehow from perhaps a continuous system environment create a candidate abstraction in some sense of the system. Could be a discretization, could be a selection of certain features. Create a model from this, and this we can then verify. And if it's not good enough, we want to reiterate on this problem of creating an abstraction. So somehow the abstraction is data-driven, right? And we want to verify it. This is what we want to do, and what we also aim to do is to provide, let's say in this case, PEC guarantees against various types of uncertainty. Let's look at an example. We want to fly this drone, right? So we do the following. We have a state of the drone. We create a controller that gets the current state and then gives an action to take. So the entity that we want to construct is this controller. Let's say this is the optimal path up to this point. And it depends on a certain wind conditions. So if the probability for like a disastrous wind gust is very low, the green one is the best one. If it's very high, the red arrow is the best path to take. Yeah? So this is some form of uncertainty that we deal with. We have a probability on certain wind gusts. Okay, now we make it more complicated. The mass of the drone might be unknown, but within some range, right? So we don't know it at this point. So now what this means is, if we have this ranges of the mass of the drone, the outcome of certain actions are uncertain, but within these sets according to the ranges of the mass of the drone, yeah? So this is the two types of uncertainty that we have, and more specifically, we have stochastic wind conditions, which we might call aleatoric uncertainty, and the mass might be unknown, which we would call epistemic uncertainty. Aleatoric because, I will specify this a bit, we have random effects, but we know their distributions, yeah? So we can deal with those, and we assume them as given. We cannot reduce the uncertainty here, yeah? Epistemic, some people also call this systematic uncertainty, means a lack of knowledge, right? So we don't know enough at this point, but we could gather more data and reduce the uncertainty about this, but we might at some point have to just deal with it. So how do we handle this? And I think I have to hurry up a bit. We create this finite state abstraction, as I mentioned. Then the model that we create is actually an interval Markov decision process, which we can analyze using the PRISM tool. And then we compute a controller that actually loops back to the continuous setting. We can guarantee the safety of this controller, the correctness of this controller. I have some more nice pictures. By the way, credit to my PhD student, Tom Bardings. I will give him more credit later, but he created those. So how do we capture this aleatoric uncertainty? Let's say if we don't know the distribution. So what we do is the following. We want to know the probability of transitioning to a certain state, and we don't know the distribution. So we use access to a simulator to sample, right? So we sample to derive these probabilities, and these samples gives us successor states, right? So we could just do a simple estimate. What we actually do is we ask a user, what is the confidence on your probabilities that you want, right? And then what we give the user is, well, we give you a guarantee that the probability of the actual probability being within these bounds, which we call P lower bar, upper bar, is greater than this beta, this confidence probability. Yeah? About epistemic uncertainty, so let's say we had a medium mass of the drone, then the outcome of an action will be leading to this green point. Now we have a very low mass, then this would be the point to go to. We have a very high mass, then this would be the point. And the obvious solution to this, if we know this information, is to put this in boxes, which account for every kind of mass that can happen here in this uncertain setting, right? So we make this method robust against any realization of the epistemic uncertainty. This is the concept of our method, and a bit summarized. What we do is we have this state system, we compute an abstraction, we compute this uncertain model, then we verify it, and the result that we actually get using our sampling-based abstraction technique is that we give a robust policy, a controller, which will actually satisfy the spec with, for instance, greater than 90% probability. So this is the type of result that we can get from these settings. Some literature, and also credit to my PhD student, Tom Bardings. As Peter mentioned, with this paper, we won the AAAI Distinguished Paper Award, and there's since then has been a couple of more papers, a journal paper and a recent AAAI paper, actually dealing with these kind of data-driven abstractions with guarantees and dealing with various types of uncertainty. Okay, moving on to safe reinforcement learning. Who knows what safe reinforcement learning is? A few. So what is this? It makes reinforcement learning safe. Safe is a very bad word here, but it means basically get a handle on what actions the reinforcement learner may take. So what this means in the end, you have your usual setting where you have an agent here, you do some actions and you observe something. You want to make this more complicated. What people have coined, this was done by people around Roderick Bloom and Bettina Könighofer a few years ago. They invented the concept called a shield. So what a shield does, it blocks certain behavior based on some model-based information, as you can see here. So we have a model here, we have a verifier, and this shield is constructed and will block unsafe actions of the agent. What I always thought, and what also has substantiated now, is that the shield is kind of a bad word, because we don't always want to say this makes it safe, but we also prevent the reinforcement learner from taking a lot of unnecessary actions, right? So we, in some sense, use this shielding to improve the convergence rate of our reinforcement learning action, and in some sense then a way to inject structured domain knowledge into our learning setting. Yeah? So we integrate a verifier with reinforcement learning that constructs and updates a shield according to new data, coming back to the adaptive scheme that we always use. And then there's a very clear trade-off between the correctness, which means the safety, and the exploration freedom of the agent. So we need to be careful about this. So what we did very quickly, we integrated, in some sense, our shield computation with state-of-the-art deep reinforcement learning, because many approaches so far were just dealing with a very simple tabular reinforcement learning methods called Q-learning. And I will talk a bit about a tool that we have later. So what we really have here is, we have from the OpenAI gym, you can use any environment and any state-of-the-art reinforcement learning, deep reinforcement learning agent. And you can integrate this with the storm model checker. So you can have some model, you should have some model, use this to compute some structured information, and then you can integrate this with the OpenAI gym. Yeah? So this is what we do on a very high level in this case. Let's look at some examples. So what happens here? And we have tons of these gridword examples. There's credit to Peter's former PhD student, Sebastian Junges, who coded the following. You give your formal environment of the MDP with some kind of information, then automatically you will generate such a gridword. This is extremely nice. So what happens here? The agent, there's a safe zone. It can move here, but it should move here. This is something bad, let's say whatever, some monster that wants to eat you, and we cannot fully see where the monster is. So if we let here the reinforcement learning agent run in an unshielded way and here in a shielded way, we can see what the difference actually is. So the pink stuff is the range of vision, so now the left one has died. The other one will stay safe as soon as this one comes nearer, right? Because we have this model-based information here, and at some point it will, and I think can wait for this, move, it will have learned enough about the behavior of this agent that it can actually go to the green area, right? So because this one is far away. Yeah, and we have tons of those examples. And I like them very much, not only because they are a bit more shiny than just showing numbers, but also because it gives us a lot of information actually how our policies were behaving. It's not only, okay, yes, no, it's more like, oh, it does some very weird behavior here. Why is this happening? What can we do about this? Yeah, so this goes a bit into explainability, but let's not go into this. Okay, so there's some literature, and I like this very much because the backbone of the shield computation was published at CAF 2 years ago, and the integration with deep learning was published at AAAI this year. So this really kind of brings the two worlds and areas together here. Good. So I have some questions that I will answer, but perhaps not, because you told me in 3 minutes I should largely stop, right? So I will be quick, but I will tell you what questions I have, and I could answer if you would be interested. So the first one is, what type of guarantees do we give? Because this happens a lot at these events that somebody says, yeah, but we give guarantees. And then so I say, what is a guarantee? So what does this mean? So it's a very kind of ambiguous word. So what we do is, if we say we have some environment and we create a model, then we need some correctness on the model. This could, for instance, be a pack guarantee on how correct the model is. And if we have this, then if we use an exact method, so we're not adding another like approximate layer in there, then the guarantee that we can give on the overall correctness of our method is a pack guarantee. This is something that we can easily do. Happy to talk more about this. Our models are mostly POM-DPs, and the main message here is that in its general setting, everything is undecidable. If we restrict to for instance, something reasonable like finite memory, then everything is decidable, but might, for instance, be NP or P space hard. Yeah, I will go through this. So a very standard problem that we look into is, if we think about safety, let's make it almost sure, right? So safety is just binary. It's safe or it's not. And actually, this is a nice thing. It doesn't make anything harder for us, because if we say it just can be safe or not safe, then what the properties that we have below this is an almost sure property, right? And these can ignore all probabilities, numerical problems. It really means we work on the transition system in the end, and the underlying problem is X time complete, and there are rather efficient methods to solve these problems nowadays. Yeah. How do we implement it? I said there's another slide. So we have a tool that we call CoolMC, a comprehensive tool for reinforcement learning and model checking. It integrates the storm model checker with the OpenAI gym, and we're still working on this. I think there will be some progress with this tool in the future, and I'm very happy to give it to you if you're interested. I don't have the link here. I have the link here. We call ourselves nowadays the Lava Lab. So you can just have a look there at this tool, and if you need support, please let us know. I wanted to talk about teaching because there are a lot of kind of fun projects that we're working on, and I just like to show them. So we have a lot of thesis projects that we did in the last years, and they're color-coded with the areas that we have been working on. And I want to mention, for instance, that this master thesis from last year, is now being published at, I misspelled this, ICLR 2023. This is one of the major machine learning conferences, and this was really just done by a brilliant master student that was working with us. So this is a lot of fun that we can integrate kind of the teaching and the education into cutting edge research here. My fun projects are the following. This was a bachelor student from some years ago. She worked with Pac-Man, and she let all her friends and relatives play Pac-Man and collected data on how these guys played. And the idea was that she would tell her peers, avoid the ghosts, eat everything, and then she basically would collect all the data, verify it, and then create an AI that could play Pac-Man 10 times better than I ever could. So that was a lot of fun. Who knows this game, 2048? Who was addicted? Okay, I wasted a lot of time with this. So a student came and wanted to play this game with some reinforcement learning external knowledge. So what you see here is his simulator. And so what happens is with this knowledge performs better. At some point the student came to me and said, I don't know where to proceed. It never converges to the 2048. Calm down, you perform much better than the stupid reinforcement learning, so you're done. So this was a very nice student and it worked quite well. Moving on, some wrapping up. So I want to basically mention my group of one postdoc and PhD students. They are all brilliant, and this kind of shows on how we try to work together. Some of them started very recently, and everything that I presented here is kind of credited to them. And yeah, I'm nearly done. So Peter mentioned that I have this ERC starting grant, and there are positions. If you know anybody who could be interested, especially for postdoc positions, I want you to work with me on Neurosymbolic AI, which means that we are hiring. So if any of the programs are of interest and you know somebody, please let me know. And finally, a summary. So what we really try to do is to have tightly integrated learning and verification/formal methods approaches that are dedicated to typical AI and robotic systems. We do fundamental research, but it goes also to applications with real-world challenges. And nowadays, you often have to state a vision. So my vision is that we can help developing data-driven systems whose decisions are known or proven to be correct. So with this, I can close, and thank you very much.
Thank you very much, Nils. I would like to open the floor for discussion, and there's a question here in the front. Maurice.
Yeah, so thanks, Nils, for this very, very nice presentation.
Thank you.
So I was just wondering, so you basically, if I understood well, all these problems have like a single optimization objective, right?
Yeah, no.
So, no.
No,
Okay.
because in reinforcement, the objective is to maximize some reward, and the second objective is to, that the probability to not crash is below a certain threshold. So this is very inherently multi-objective problem.
Okay, so then, so yeah, because safety often is a trade-off.
Yeah,
right? So,
yeah.
So you can give then as an answer how to fine-tune based on which of the objectives you give more value to?
Yeah, this is a very good question. So we didn't do this in a structured way. So we usually just say, optimize this objective subject to that this objective is satisfied, which is then a clear cutoff. What we did, for instance, the safe reinforcement learning setting was to do things like have this shield in place to always make sure that the specification is satisfied, but at some point phase it out and assume that the neural network has now learned to behave safely, right? And this kind of, I would say, an implicit getting a trade-off, because then what happened, there would then happen unsafe actions, but way less than in the beginning. So we had kind of a learning-based trade-off, but we didn't do this in a structured way. So we didn't look like at the real parity curve of these methods. But this is, of course, something very interesting to look at, yeah.
Thanks.
Yeah, thank you.
Any further questions? In the back on the left. Laura.
Hi, thanks.
Hi.
It was a very nice talk. I still wonder, like, after listening to your talk, so what exactly is safe then?
Yeah. For me, safe is that you satisfy a given specification, perhaps with some confidence probability. I really struggle with finding the right wording often. And I think also that safe is hugely overused in the literature. Yeah. Does this already answer your question? Okay. Yeah.
Okay, there is another question also in the back on the left.
Thank you very much for this enlightening talk. I was wondering, do you have a specific or maybe a more systematic approach to arrive at the specification that encodes what maybe is safety in a specific setting, or maybe even has a richer, encodes a richer corpus of knowledge?
So is your question basically how we can actually find the right specification for a certain setting?
Yes.
Yeah, so I have not worked on this, so of course I'm aware of a lot of work like specification mining, LTL learning and other approaches. I think this is extremely important and I'm very interested, but I have not worked on this yet. Yeah, okay.
Other questions? Then I have a question.
Yeah.
So you use under the hood several types of model checkers. Throughout the talk you mentioned a couple of them. What's the main challenge to them? If you would, let's say, on your point of view, AI, safety, reinforced safe RL, what is the main issue that in this model checking community is lacking? Or is it scalability? Is it functionality? Is it something else?
It's of course, in some sense, all of it, but also there a lot of progress has been made in the last years. So if I want to make this a bit more specific, I would unspecifically say scalability. But then if you look at it, what is often really the problem is that, for instance, there's no very structured approach in formal verification to deal with certain features and to kind of find out what features are important to satisfy the specification, which would, for instance, enable us to perhaps ignore large parts of the model or to find an abstraction that is meaningful to the tasks that we are doing. And specifically to my research, often various shapes of uncertainty are also an issue, because right now, Storm and Prism can deal with these interval probabilities, but there might be more accurate shapes to capture the uncertainty. So this is something that I think there will be some progress made in the future.
If there are no further questions, then I would like to thank Nils for a great talk.
Yeah. Thank you. Thank you very much.